computer. So when I do publish the recording, it will not be in Zoom in Canvas. It'll be in the in this week's module. Okay, so that's where you'll end up finding it. It'll probably be later tonight when I post it, because it takes a while to process the recording. And you won't need a passcode for these recordings from now on. I think that might work better for most people. Okay, so and one thing I may end up doing also, maybe not today, but in the future, is just record one of my 2 statistical literacy sessions. I teach back to back. I teach one, of course, at this time and one at 3:30. So I might just record one of them per day and then post that recording for both classes. Okay, so let's get to the PowerPoint and get started. Okay, so this chapter is called Understanding Probability and Long-Term Expectations. Now, originally, and I guess in a previous version of this book, this is the 4th edition. It used to be chapter 19. So if you do, hopefully you don't have an earlier version, but if you do, this is not, that book may show chapter 16 instead of chapter 14. So, okay, so again, we'll start off with some of these thought questions. So we may have 2 different types of questions regarding probability. For example, we may have a probability that has to do with maybe flipping a coin so many times, and we want to do an experiment and find out how many times we get heads, maybe in 100 flips of the coin. We also have the type of probability where that you're just sort of guessing at the probability of maybe owning a home or something like that. So these are, in this book, they talk about these 2 general types of probability, which we'll give some names to them in a second. It says here, explain what it means for someone to say that the probability of his or her eventually owning a home is 70%. So can somebody, maybe based on what you think the definition of probability is, can somebody say what this might mean? Anybody?
It's a 70% chance.
Okay, 70% chance. Okay, and what does that really mean? 70% chance.
They're 70% more likely to have it than the 30% that don't.
Okay, now you're talking about a particular person?
Yeah.
Okay, so if you randomly select somebody, right, from, let's say, a population, right, and you ask them what's the about eventually owning a home, there's a 70% chance that that person will eventually own a home. Is that what you're saying?
Yeah.
Yeah. Okay. I would add one more definition. So if you randomly select somebody, what's the probability that person will eventually own a home? 70%. Right. So you're randomly selecting one person and asking this question. A probability could also mean that approximately 70% of the population will eventually own a home. In other words, it's the proportion of the population that eventually owns a home. So both those definitions will work with probability. Randomly selecting one person or the proportion of the population. Both those things mean the same thing. All right, it's asking here about what's wrong with this partial answer to that question. The probability that I will eventually own a home, or if any other particular event happens, bad English, is 1/2, because either it will happen or it won't. What's wrong with that reasoning?
It doesn't explain the variables that tie into it because it just says any other particular event happening.
Okay, all right, sure. So you're saying there might be more than one reason, right? Right? More than one possibility? As, right? Owning a home.
Yeah.
Well, I think what they mean by this is that not just owning a home, but anything. Let's say you have two choices, right? There's two choices for anything. It could be flipping a coin, it could be owning a home, it could be whatever. There's two choices. Something's going to happen or it's not going to happen. So in this case, they're saying the answer should always be 1/2. It's 1/2 chance it's going to happen or 1/2 chance it's not going to happen. So the question is, now you could see in the previous slide, it said it was a 70% chance of something happening. Why can't you just say it's 1/2 chance? Because it's either going to happen or it won't happen. That's what they're asking here. Why does it have to be something other than 1/2?
Is it because it's not the true probability?
Okay, all right. BB, can you give me a little more detail about that? What do you mean by that?
Like when you take a half and put it as a percentage, it's 50% chance on everything. But we saw before there was a 70% chance for the one person to own a house.
Okay, all right. So, but can you picture somebody saying something like this? The probability that I will eventually own a home is 1/2 because it's either it will happen or it won't. And it's equally likely it will happen or it won't. So why is this reasoning not quite right? I mean, you can picture somebody saying this, right? You can picture somebody saying, well, it's just 1/2. Well, the answer is that not all events are like this, where it's strictly that it's not necessarily so that the probability that will happen or won't are equally likely. Okay, let me give you an example. If you have a die, right, a 6-sided die, you've seen them before with the dots on them, right? One dot all the way up to 6 dots. All right, it's a 6-sided die, and you roll it. The question is, what's the probability of getting a 1? What do you think the answer it must be? You're rolling a die. What's the probability of rolling a 1?
1 out of 6.
1 out of 6. Now, you could say, well, the probability of rolling a 1 is 1 out of 6. What's the probability of not rolling a 1? What do you think the answer to that is?
5 out of 6.
5 out of 6. There's 5 other possibilities out of the 6. You see, it doesn't have to be that there's an equal probability of something happening or not happening. It could be unequal. And that's really what they're saying here, all right? Because sometimes people will say something like this. It's either going to happen or not, therefore it's at 1/2 chance. Well, that's not necessarily true. Some probabilities of something happening are less than 1/2 or greater than 1/2. Now, what do you think is the lowest probability that you could possibly have? Give me a number. What's the smallest probability that you can have for anything, any event? If you're not sure something's going to happen, what's the smallest chance that it can happen?
0.
0, right. 0 means impossible. It's impossible. Now, there's not many things in life that are impossible, but that's what it means. So you can't have a negative probability. You can't have a probability that's less than 0. What's the largest probability that you can have?
100.
100 what? If you're going to use the word number 100, what do you have to put? What word do you have to put next to it?
Percent.
Percent, right? Or if it's not a percent, it would be, what's the number? We're not expressing it as a percent. The number 1. 1. The probability of 1 means absolutely certain it's going to happen, right? Absolutely certain. So probabilities are always between 0 and 1. It can never be a negative number. It can never be a number bigger than 1. So if you ever do a calculation, let's say I ask you to do a calculation, and you get a negative number or you get a number bigger than 1, you know you did something wrong. All right, always. It's never outside of that range between 0 and 1. And most probabilities are between 0 and 1. All right, here's another question. Why do you think insurance companies charge young men more than they do older men for automobile insurance, but charge older men more for life insurance?
Because there's more of a probability of a young man driving recklessly,
Good.
and older men are die younger. I mean, not die younger, but like die younger than women.
Okay, I think they want you to compare it to younger men. Let's forget about the gender difference, about the age difference.
More likely to die.
More likely to die, right? Older men are more likely to die. Exactly right. Exactly right. So your reasoning is absolutely true. So for automobile insurance, younger men tend to be in more accidents than older men. Not necessarily, but depending on the ages, but typically. So they get charged more for their premiums. And for life insurance, older men are closer to death in overall. Not true for everybody, but overall closer to death than younger men are. So therefore, there's a more likely chance that an older man's going to die, and the life insurance company has to pay up. That's why they charge more. All right, very good. How much would you be willing to pay for a ticket to a contest in which there was a 1% chance that you can win $500 and a 99% chance that you would win nothing? Now, it's saying, what would you be willing to pay? It would be the maximum that you'd be willing to pay. What do you think the answer to this question is?
Nothing, because there's less of a chance of you winning.
Okay, nothing. All right. So you would say you're not willing to pay anything for this ticket?
Yeah, because yeah, I'm not gonna lose my money.
Okay. I will not invite you to any lottery that I ever set up. Anybody? It's good reason. I like your reasoning, but you're very conservative. Anybody else? Anybody else who may be a little more, may want to take on a little more risk?
$20.
20 bucks, okay. And how did you come up with the $20?
I'm comfortable losing it.
Oh, okay. All right. Interesting. And
Say
anybody,
$5.
how much?
$5.
$5. And how did you come up with the $5?
So it's like $500 is 100% out of 500. So for every like 100, that's $1. And I don't know how to do the math, but it just made sense in my head.
Good, 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 good. Okay. Well, you are correct. The maximum you should pay is $5. Now, the reasoning is what? The reasoning is that over the long term, if you have a 1% chance of winning, that means out of 100 times that you play this game, right? You would win once over a long period of time. That's just your average, 1 out of 100. So you're going to win once out of 100. You're going to lose in 999 of those. 99 out of 100 times. Correct? So the way to do it mathematically that we're going to learn is we're going to take our probability. We'll convert this 1% into a decimal, 0.01, and we're going to multiply that by the winning amount. But we also have to do the other thing too. We have to look at the 99% chance of not winning. In this case, you would win nothing. All right. In other words, you're not going to lose anything, not going to win anything, 0. And you're going to multiply to 0.99, which is 99%, times 0, which is 0, right? So 1%, 0.001 times 500 is $5. And that's how you would come up with the answer. Now, I like the other answers, especially in both answers. All 3 answers are good. the person who mentioned the $20 said, because I'm willing to spend the $20. Well, that certainly comes into play, doesn't it? What are you also willing to spend? Now, in this case, you know, over the long term, if you were a person who was using math to do this problem, you'd say $5. You know, I'm not willing to spend more than $5 because that's my long-term expectations of what I would win. But some people might be willing to spend more to play this game, and that's fine. But this is the, how shall I say it? It's the economic, it's based on economics. Economics would say it would be $5. No more than $5 should you spend, you know. But hey, if you want willing to spend 20, go right ahead. All right, let's look at two distinct definitions of or interpretations of probability. Now, first one, the probability of winning a lottery based on buying a single ticket, we can actually calculate that. We can calculate that. There's ways of doing that. And we're not going to spend a whole lot of time in this course doing that. If we were in again, a traditional statistics course, we would spend a couple of weeks on probability. But in this course, we're just going to give you a sort of a taste of it, all right? Just so that you know what it means. So this is one way of calculating this. And by the way, this is similar to the idea of flipping a coin and saying, what, you know, if it's a fair coin, what's the probability of getting heads? Well, there's only heads or tails, right? So you'd say half because it's a fair coin. I gave the example of rolling a die. What's the probability of getting a 1? Well, it's 1 out of 6 because there's 6 equal 6 sides with different number of dots on them. And each side is equally likely to come up when you roll it. So that is, those calculations can be done before you do anything. The other type of probability is basically where you're just assessing based on your personal beliefs, right? The probabilities. The problem with that is, as we'll find out on Wednesday, is that sometimes our brain is not set up to judge probabilities correctly. We may underestimate or overestimate probabilities if we're just guessing at them or basing them on our own experience. Okay. So the first type of probability can be done through what's called a relative frequency approach. What does that mean? That means we can repeat now, if we know ahead of time what the probability of an experiment is, we can repeat the experiment many, many times, and we can count basically the number of times we get a certain result. And for our probability calculation, that would be the numerator of a fraction. That would be the count of the number of times a result will occur. And our denominator would be the number of times that we repeated the experiment. For example, if we rolled a die 100 times and we wanted to know how many times would we get a 1, well, theoretically, we should get a 1 every time we roll it 6 times. But we won't necessarily, and that's what is that probability? That's 1 out of 6, that's 16.7%, I believe, okay? So 16 or 17 out of 100 rolls of the die, we would expect to get a 1, but we wouldn't necessarily get that as a result. We might get 14, we may get 21s, it depends. So this is called the relative frequency interpretation. We just repeat an experiment, rolling a die, flipping a coin, maybe asking a question in a survey. We repeat it many, many times. All right, and we'll get a result. We'll get a result. We're not guessing at it. This is a result based off of an experiment that we're doing. All right. Some of these types of experiments, we can guess the probabilities ahead of time. Other types, we can't. Like the second example here, commuting to work daily and observing whether a certain traffic signal is red when we encounter it. Well, the only way to come up with a probability with this is that we do it a little bit of an experiment. We have people commute and go through this traffic light or encounter this traffic light many times, and we count the number of times that we observe it being red. And divide that by the number of times that we ran the experiment. And that would be what's called a relative frequency, or it could be a proportion, another way of saying it. We could test people in a population and observe whether they carry a gene for a certain disease, right? We can count the number of babies that are male versus female when they're born. These are all based on a relative frequency approach. Okay. Now, in statistics, this is what we use. All those tables that we did, you know, in chapter 12, remember those tables, and we were calculating things like odds ratios and risk and all of that. They were all counts. Okay, and we used the relative frequency approach to come up with what? The risk, or we can also call it the probability, right? Or proportion. It all means the same thing. Now, with repeating an experiment many times, we will come up with a good estimate of the probability of something happening. The way we know this is that we can do an experiment. For example, flipping a coin. You know, if we flip a coin 10 times and we want to count the number of heads, well, we can have quite a variation in what people will come up with in 10 flips of the coin. Some people will get 6 heads, some people will get 8 heads. It'd be rare to find somebody get 10 heads, but it's possible. But if we ask somebody to flip a coin 1,000 times, then it's going to be pretty close to 50% heads. So the more flips of the coin that we do, the closer that we get to the true relative frequency, the true probability. Okay, and that's one of the hallmarks of statistics, is that through repeating the experiment many times, we have a good estimate of the probability of something happening in a population. Okay, here's an example here. Results for the relative frequency of male births. Now, if it's known that the long-term probability or long-term relative frequencies of males in the U.S., born in the U.S., is a little over a half. And if we just actually watched babies being born and just seeing who were males and who were females, well, if we, the more weeks we watched, the closer the proportion would be to the actual long-term relative frequency. In this particular experiment, somebody watched for a week and found that there was 40% of the babies were boys. Over 4 weeks, 47%. Over 12 weeks, 53%. And it jumps around a little bit. But the longer we watch the babies, the longer number of weeks we watch them, the closer we're going to get to the actual portion. Okay. Any questions about that? All right, because without this idea here of long-term relative frequency being a good estimate for the probability for a whole population, we wouldn't be able to do very much with statistics. Basically, we wouldn't be able to take a survey result and say something about the population. Okay. So here are ways of determining the probability of an outcome. Sometimes it's making an assumption about the physical world. Okay. For example, if for flipping a coin, we assume that the coin is a fair coin. So that's why we come up with the probability of flipping a coin, of getting heads once, is 1/2. We're making that assumption about a coin. Or again, we can run if we don't know this ahead of time. For example, we have an election tomorrow. We don't know the actual percentage results yet, right? We can guess at it. We have polls that might give us an idea, but until the results come in, we don't know the answer. So we do what's the relative frequency approach, right? We have people vote. We count the number of votes. You know, Trump gets a certain number, Biden gets a certain number, and that's how we come up with the winner. All right. So this is what I just said is the relative frequency approach. All right. So one approach to determining probability is making an assumption, and the other is to actually do an experiment. Now, here's a summary of this relative frequency approach. All right. Can be applied when the situation can be repeated numerous times and the outcome observed each time. So a survey is a great example of that. Number two, the relative frequency should settle down to a constant value over the long term, which is the actual probability. Okay, again, the idea is repeat the experiment many, many times. And after some time, we'll notice that the probability is getting closer and closer to some long-term value. This approach does not apply to situations where the outcome one time is influenced or influences outcome the next time. Now, what does that mean? If we repeat an experiment over and over again, we assume that one application of the experiment is independent of another application. That is, the probability of something occurring does not depend on what happened previously. If we flip a coin 100 times, the 80th time we flipped a coin should not be influenced by the previous 79 times you flipped the coin, as long as your arm doesn't get tired, right? It should each flipping of the coin should be independent, should have nothing to do with any other repeat of that experiment. If they are related, then this approach doesn't work. We have to come up with something else. In this course, we're not going to be dealing with that situation very much. All right, we're not going to talk about where there's not a lack of independence for each person in a poll, for example. All right, we're not going to talk about that. The last one says cannot be used to determine whether the outcome will occur on a single occasion. It can be used to predict long-term proportions, times the outcome will occur. Now, what does that mean? Well, a probability really talks about a long-term expectation for something to occur. All right, it may not apply necessarily to a particular person. For example, if let's think of some example. Let's say people who drink orange juice every morning, the probability of them getting a cold is 10%. While somebody doesn't drink the orange juice, the probability of getting cold is 30%. Okay, that may be true for a large population, but it may not be true for you. All right, it could be that you drink orange juice in the morning, but then you eat junk the rest of the day and you don't have a balanced diet, and so you're more prone to catch a cold, that sort of thing. So that, individual circumstances have to be determined to really come up with your own probability of something happening. So probability deals with the whole population, not necessarily for one person. Okay, any questions about that? Because that's important. Some people, what they do is they hear about a probability and apply it to themselves, and it may not really apply to them. All right, personal probability interpretation. Well, again, this is basically the person believes the event will happen, based on their own experience maybe, or just guessing at it. It's not a very scientific way of coming up with a probability. All right, somebody may be asked, what's the probability of finding a parking space downtown on a Saturday? Well, unless you run an experiment, you're just going to guess at it, right? Based on your own experience. You might find it's a higher probability than finding a parking space on a Wednesday, just because people aren't, maybe people work and they're not working, that sort of thing. So it's a personal choice here. And again, we don't, as far as statistics is concerned, we want to rely less on this way of measuring probability and rely more on the relative frequency approach. Because it's very easy for people to come up with their own opinions about probabilities. Now, you still have to make sure the probability is between 0 and 1, right? And there must be a coherent explanation for it. But again, it's more of a guess than it is based on experience. All right. Now, let's apply some basic probability rules. Now, again, if this is a more developed course in statistics and probability, we would go into this more mathematically, but we're just going to deal with very basic ideas here. So hopefully these rules that you see in this chapter will be good enough for you to answer probability questions. Again, the probability questions that I can ask are kind of limited. There's not that many that I can ask you. Then anyway, let's assume the following. It says if the probability of a single birth resulting a boy is 0.51, and if we just assume for now, we'll just have two genders, males and females. Assume that the probability of a girl is going to be 0.49. Now, why is that the case? If we think of all possible outcomes in an experiment, what's the experiment here? If we pick a child at random, a baby at random, is it a boy? Is the baby a boy? Is the baby a girl? All right. Well, if the probability, if there's only two choices, and the probability of the boy is 0.51, the probability of the girl has to be 1 minus 0.51. Because remember, probabilities have to add up to 1. Why 1? 1 means certainty. If we consider all possibilities for a particular event, then if we add up all the probabilities, that must be equal to 1. That makes it certain. It's certain that one of these things has happened. So if the probability of a boy is 0.51, and if the only other choice is a girl, then 1 minus 0.51 must be the probability of a girl. Because why? Because 0.51 plus 0.49 is equal to 1. And 1 means certainty. So it's absolutely certain that if a baby's born, the baby's either going to be a boy or a girl. All right? Do you get the idea? The probabilities have to add up to 1 for all the possible outcomes. Here's another idea in probability. If two outcomes cannot happen simultaneously, they are said to be mutually exclusive. The probability of one or the other of two mutually exclusive outcomes happening is the sum of their individual probabilities. All right, so what does that mean? Well, let's go back to the boy-girl, right? If a child is born and there's only two outcomes, those outcomes are mutually exclusive. That means the baby's either a boy, the baby's either a girl, all right? And again, we're just making this assumption. We're not going into other possibilities, all right? Let's make it very simple. Boy, girl, those are the two outcomes. They're mutually exclusive. Either the boy is either the baby's a boy or the baby's a girl, all right? That's what we mean by mutually exclusive. Two outcomes cannot occur simultaneously. Grades, another good example, right? You're either going to get, let's say you get an A or you don't get an A in a course. All right, let's make those the two possible outcomes, A or not an A. Well, you either get an A or you don't get an A. You can't get both. They're mutually exclusive outcomes. So therefore, the probabilities have to add up to 1. All right. So we add their probabilities. So here's an example. And I guess we're going to add some other grades here. So let's say the probability of getting an A in this course is 50%. The probability of getting a B is 30%. And the probability of getting an A or a B is what? Well, we're not considering any other grades, C, D, F, right? None of those. Well, because these two grades, A and B, are mutually exclusive, they can't occur at the same time for the same person. And when I ask what's the probability of getting an A or a B, it's the sum of the probabilities of getting an A plus the probability of getting a B. So we simply add these two probabilities. 0.5 plus 0.3, which is 0.8. Now they did it as percentages, but We just added as a decimal, 0.5 plus 0.3 is 0.8. In other words, there's an 80% chance of getting an A or a B. Now, what's the probability of getting a C or less? Okay, and oops, sorry about that. Well, that's all that's left, right? You either get an A or B, or you get a C or less. There's no other grades. So that third category has to be the remaining 20%. Why 20%? Because getting an A or getting a B or getting a C or less is all the possibilities, which is equal to 1 or 100%. We have 80% representing the A or B. What's left must be getting a C or less, which is 20% or 0.2. All right. Does that make sense to everybody? What mutually exclusive? And the key words when we use the mutually exclusive is or. We're saying what's the probability of getting this or getting that? Getting this A or getting a B. When we use the word or, we add the probabilities. That's very important to understand that, because some people use addition when they shouldn't. But when we use the word or, like right here, getting an A or a B, right, is 80%, we add. So that's the key word, or. Here's the other rule that you have to know about. If two events do not influence each other. Now, what does that mean? The two events could occur at the same time, but they don't influence each other, which means knowledge of about one of them does not change the probability of the other. Let me give you an example. All right. Let's say you wake up in the morning, you don't check technology or anything, you just take a look outside and you think, all right, I think the probability it's going to rain is it's full sunshine. I don't have any other information. The probability it's going to rain is 10%. I can't say 0 because there's always a chance it could rain, but I'll say 10% because it doesn't look likely. But then you start looking, then later on you look out the window and somebody's walking their dog. All right, you see somebody walking their dog. Now, does walking the dog change the information about whether it's going to rain later or not? Well, unless the dog is wearing a raincoat or something, no. There's that information that's being conveyed by the person walking the dog does not change the probability of it raining. So we say there's two events are independent. The event of it raining and the event that somebody's walking their dog. They're independent. They have nothing to do with each other. They can occur at the same time, but they are independent of one another. All right. Now, here's the deal. If two events are independent, the probability that they both happen is found by multiplying their individual probabilities. And this is where we would use the word and, A-N-D. We would say the probability of A occurring and the probability of B occurring, basically at the same time, is equal to the probability of A times the probability of B. We're making the assumption that A and B are independent of one another. If they're not independent, by the way, we can't multiply those individual probabilities. We have to come up with something else. There's another formula, but we're not going to be dealing with that in this course. So here's an example. A woman, let's see, what does this say here? Woman will have 2 children. All right, a woman will have 2 children. Bad English again. Assume the outcome of the second birth is independent of the first birth, and the probability of a boy is 0.51. Again, very terrible English. I didn't write this, by the way. Then the probability of a boy followed by a girl, let's say the first child is a boy, and the second child's a girl. Let's say we don't know anything about the births yet, and we want to ask the following probability. What's the probability that the first child that's born is a boy and the second child is a girl? We don't know anything about it. The only way to do this is, well, the first child and the second child are independent of one another. The births of the two are independent. We assume that. So the probability that of the boy first is going to be 0.51. The probability of a girl's second is 0.49. And since these are independent of one another, these two events, we multiply the probabilities and we come out with almost about a quarter. So the probability that you have a boy first followed by a girl, right, is 1/4, 0.25, approximately. Any questions about that? That's what independence means. Here's the last rule. All right, I think it's the last rule. And I think this is sort of common sense. If the ways in which one event can occur are a subset of those in which another event can occur, then the probability of the subset event cannot be higher than the probability of the one from which it is a subset. All right, that sounds kind of complicated. What it really means is, if you have picture a population, and picture that within that population there's a smaller population. Well, if we're interested in the small population, the probability of selecting somebody from the small population has to be smaller than from the larger population, because there's fewer people in there. Doesn't that make sense? So you have a larger population, you have a smaller population inside that big population. We want to know what's the probability of selecting somebody from that smaller population. It has to be less than the probability of selecting from the whole population. All right. So they have other examples here too. Here's somebody who says they're 18 and they're speculating whether they will get married in the future, and you come up with this probability that you will eventually get married and have children is 75%. Okay, so you have the probability of getting married, and then you have the probability of getting married and having children. Now, which population is bigger? The group of people who are getting married, or the people who get married and have children? Which one is bigger? I hope I didn't lose you on this one at this point. Think of people who get married, and then think of people who get married and have children. Which population is bigger?
People who get married.
That's right, because it includes what?
Those that have children.
People have children, and who else?
People who don't have children.
People don't have children. That's correct. So the people who get married and have children, all right, are a subset of the people who get married, because the people who get married include people who don't have children. So if we said the probability of a person who gets married and have children is 75%, the probability of a person getting married has to be at least 75%. It can't be smaller than 75%, because it includes more people. Okay? That's what rule number 4 is saying. All right. This one looks a little complicated, right? Now, some of you who are math oriented will be okay with this, and but those of you who get a twitch or two when they see symbols like this, don't worry. There'll be ways of of working with this without using all these symbols. But let me explain. It says a probability an outcome will occur on any given instance is P. So we're using the small letter P to represent the probability of something happening. All right, there you go. Now, what's the probability of it not happening? It's got to be 1 minus P. For example, if P is 20%, then 1 minus P is 80%, because 1 minus 0.2 is 0.8. All right. Everybody clear on that? If the probability of something happening plus the probability of it not happening has to be equal to 1, because that's certainty. Now, we assume that each time an outcome occurs, it's independent of all other outcomes. We're going to make that assumption, like flipping a coin or rolling a die or something like that. So the question is, what's the probability of this outcome not occurring on the first time you do the experiment, but does occur on the second try? Well, if it doesn't occur on the first try, the probability is 1 minus p, right? Because p is the probability that it will occur, that outcome. But if it does occur on the second try, the probability is p. So the probability of it not occurring on the first try, and when you see the word but, that also means and. Oops, sorry. Backwards there. So you see the word but, it also means and. All right, so think of multiplication. The probability it doesn't occur on the first try is 1 minus p, and the probability that it does occur on the second try is p. Then the probability of both those things occurring is 1 minus p. Again, I need to take my hand off the mouse. So the answer is 1 minus p times p. So what this little chart here is showing, again, this is more for the math people, the people who like math, is what is the probability of the outcome of, let's say you're running an experiment over and over again. Let's assume, for example, it's rolling a die. Let's say rolling a die, okay? So the chance of rolling a 1 is 1 out of 6, 1/6. And the chance of you not getting a 1 is 5 divided by 6. So what we're interested in is what's the probability of rolling a 1? Well, if we roll it once and we get a 1, well, that probability is 1 out of 6, right? That's p. So you can see that right here. If we get the 1 on our first roll of the die, well, we get p, which is 1 out of 6. What if it takes us 2 tries to get a 1 out of 6? Or excuse me, to get a 1 when we roll a die. Let's say first time we roll a die, we get a 5, and the second time we roll a die, we get a 1. Well, what's the probability of getting your 1 on the second time that you roll the die? Well, the first time has to be something other than the 1, so it's going to be 5/6. That's your 1 minus p. And the second time, when you do get the 1, it's going to be 1 out of 6. So the answer is going to be 5/6 times 1/6, which is 5/36 when you do the math. So that's how this works. This is saying, well, what's the probability of getting rolling the 1 on the third try? You're getting something other than the 1 on the first two, and you're getting a 1 on your third try. Well, the first time you roll the die, you get maybe a 4. Second time you roll a die, maybe you get a 2, and then you finally get your 1 on the third try. So the probability of not getting a 1 is 5/6. The probability of not getting a 1 is 5/6. The probability of getting a 1 is 1 divided by 6, and then you multiply those 3 fractions and you get your answer. All right, so this is sort of what they're talking about here. It's a bit advanced in the sense of the symbols, but if you understand the concept, you don't really need to memorize these symbols. So here's a practical example. All right, again, a baby is born. Is the baby a boy? Is the baby a girl? All right, and it says here we're interested in finding the probability of getting a girl. All right, so this the 1 here represents we get the girl the very first time a baby is born, so we know the probability of a girl is what? 0.49, because we know the probability of a boy is 0.51. All right, so that's the probability of getting the girl on the first try. What if you have 2 kids? What's the probability of getting the first girl on the second as the second child? Well, the first child's going to be a boy, it's 0.51, and the second child's a girl. We multiply 0.51 times 0.49, we get this number here. We saw that example earlier. What if we had 3 kids and we wanted to know what's the probability of getting the first girl on the third try? Well, the first 2 children are going to be boys, that's the 0.51 times 0.51, and the third try will be our girl, which is 0.49. We multiply these 3 numbers together, and we get 0.1274. All right, so this is an application of the idea of independence, all right, where we're multiplying probabilities. And we're also using that rule of something not being an outcome. That is, if a boy is, if the probability of a boy is 0.51, then the probability of not a boy, which is a girl, is 0.49. We subtract 0.51 from 1, and we get 0.49. Okay, so that's what they're illustrating here. Hopefully for many of you, this makes sense. If this is kind of doesn't make sense to you, don't worry about it so much because we're not going to be, if I ask a question on a test, it'd be like one question. Or something like this. All right. Now, if you go back to the previous chart, this one here, notice that they grouped these terms together. 1 minus p times 1 minus p, for example, is 1 minus p squared. You have here 1 minus p times 1 minus p times 1 minus p, which is 1 minus p cubed. So you can see the exponents going up. And that's what they mean by 1 minus p to the n power. N power means how many times does the event not occur? And we use that as the exponent. And then the probability of the first time something happening is going to be 1 minus that. So this looks like a very complicated calculation, but it really isn't. For example, suppose the probability of being infected with something, or I guess HIV here, God forbid, is 1 divided by 500, 0.002. That means the probability of not being infected is 0.998, right? 1 minus 0.002 is 0.998. Suppose, and you want to know the probability of infection in a second encounter, I guess, with somebody who's HIV, it would be 1 minus 0.002 squared. All right. Now, this formula, if it doesn't make sense to you, you can simply do this calculation here. All right. If you're not going to be infected on the first encounter, that's 0.998. And then on the second encounter, being infected is 0.002. You multiply those two numbers together and you get the same answer as if you use this formula. So for those of you who like formulas, you can use this formula. For those of you who hate formulas, just use the logic here and you get your same answer. Okay. So this is called accumulated probability. The idea of repeating an experiment many times and looking for the first time that an outcome occurs. All right, now we're going to get to, let's see how we're doing with time. I guess we're not going to get to too many of the problems at the end of the chapter, but we'll go through some of them. All right, the last concept we're going to talk about today are what are called long-term gains, losses, and expectations. By the way, this little section here is very practical because it's dealing with what are your expected results over the long term. And you're going to be using typically money or something like money and probabilities to come up with your answer. That was what we used before when we were looking at that game, right? The one where we came up with $5 was the maximum that you should be spending on a game of chance. But let's look at this situation here. This has to do with insurance. So suppose customers are charged $500 per year. All right, all customers are charged $500 per year. 10% of these customers, let's say over the long term, typically submit a claim. And let's just, for simplicity, say that every time they submit a claim, they'll be paid, 100% chance they'll be paid $1,500, right? This is a far-fetched example, but suppose this is the case. So there's a 10% chance that they're going to submit a claim and the claim will be paid, and it'll be paid $1,500. And the $1,500 goes from the insurance company to the customer. So the customer's paying the insurance company $500 per year. That's what's called a premium. And then if they have to use their insurance, they will be paid $1,500. But there's only a 10% chance that they're going to have a claim during the year. So the question is, what is the average gain or loss for the customer? All right. Now, if this was a smart insurance company, this arrangement would mean they would make money from it, right? Just like if you go to a casino and people spend money on these, slot machines or games or whatever they're playing, a casino would not last very long if it didn't make money. So the odds have to be such that they make money, and that means on average, customers lose money. It has to be that way, otherwise the casino goes out of business. It's the same thing with the insurance company. Insurance companies have to make money. That means over the long term, customers really lose money when they have insurance. Now you might say, well, what's the point of having insurance? Well, insurance could wipe you. I mean, if the insurance is covering something that could wipe you out financially, or involve you with some litigation, somebody sues you, and you could lose everything. Yeah, you probably want the insurance, like car insurance, right? So, or it might be required, obviously. So the question is, how much can the company expect to make per customer? Well, this is the way it's set up, right? When the company makes money, we have to think about money that's coming in to the company and money going out. And the difference between those two is profit, right? Revenue coming in, expenses going out, charges going out. You subtract those two, you get your gains, and it better be positive. All right, so we have to look at two cases here. A claim is paid, a claim is not paid, okay? All right, what's the probability that a claim gets paid, or you have a claim? 10%, right? It says it right here, 10% chance that the person will submit a claim in any given year. So that's a chance. We assume again the claim's going to get paid if they submit the claim. Now, if they submit a claim, how much does the company expect to gain from that? Well, they're getting $500 from the customer, but they have to pay $1,500 back to the customer with the claim. So the company's taking in 500, they're paying 1,500. That means they have to pay a net of $1,000. Does that make sense? Yeah, they're taking in and we're not considering anything else like interest or anything like that. We're just assuming these two numbers are subtracted. So $500 coming into the company, $1,500 is going out of the company. They're losing, company's losing $1,000, but there's only a 10% chance of that happening. Now, if a customer pays the $500 and they don't have any claims for the year, which is 90% chance, then the company makes $500 from that person, right? Because they took in 500, they didn't have to pay anything. Is everybody clear about this net gain? So how do we calculate the average gain, the expected gain over the long term? Well, we would multiply the probability times the amount of the gain for that scenario. The scenario, claim is going to get paid. 10% chance of the claim. Negative 1,000 is the amount, the net amount for the company. So 10% of negative 1,000 is negative 100 when you multiply this. But you have to also add to that, because this is the mutually exclusive part of it, the probability of not having a claim paid. Well, there's a 90% chance that the claim is, there's no claim, and the company makes 500. So you multiply those two together. $500 times 0.9 is $450. So this is 450 positive dollars coming in, expected dollars coming in, minus 10% of 1,000 is minus 100. So 450 minus 100 is $350 per customer. That is the average gain per customer. And it better be positive, otherwise this company is not going to last very long. Now let me ask you something. Per customer, what's the average gain or loss from the customer's perspective?
They gain 1,000.
From the customer's, they gain 1,000, but it only has a 10% chance. The average customer, overall, what's the average customer gaining or losing? Now you're saying they're losing 1,000. But that's just part of the whole thing here. Well, it has to be $350 loss per person on average. Because this is what we call a net, this is a situation where the customer and the company come together, and whatever one gains, the other loses. It's the same amount. Now, we're not talking about any additional monies that the company wants to make. They may pad this, right, with some sort of additional money that they want to make. But this is strictly looking at it from this point of view. If $350 is the average gain per person, per customer, for the company, that means how much would one person lose on average over the long term? $350. All right. They're charged $500, remember, for the insurance. If they kept this insurance for 100 years, their average loss per year would be about $350. That's what they're saying. All right. So they didn't lose the full 500. They lost about $350 overall, because there would be some years where they would have a claim. Okay. That sort of makes sense. So for example, if there was 1,000 customers, then the average gain, total average gain, would be $350 per customer times 1,000. So it would be $350,000 would be the expected gain for the company. And then the group of customers overall would lose on average $350,000, not per customer, but for the whole group. The money has to come from somewhere. If the company's making $350, where's it coming from? It's coming from the customer. See what I'm saying? Does it make sense? And it's a long-term average. There'll be some years where a customer gains money, like you mentioned, $1,000. They gained 1,000, but it should only happen about 10% of the time, right? About most of the years they're going to be losing 500 because they don't have any claims. So the person who mentioned the $1,000 before, does that make sense to you? What I mentioned?
Yeah, I just mixed it up.
No, it's not a mix-up. It's actually a good point to make, because it's very easy to confuse what an individual experiences as opposed to what a group of people experience. But I'm glad you mentioned that, because I think it hopefully clarified to you what this $350 means. So it's positive $350 on average per person is the gain for the company, and over the long term, an average of $350 loss per person. And when I say loss, I mean out of the $500 that paid, $350 of it it's gone. But that's what you get for paying for insurance, right? It's not a money-making venture for most people. You're doing it because you don't want some horrible thing to happen, like somebody suing you if you get into a car accident, or you own a home and somebody slips on ice and breaks their leg on your property. They could sue you. You could lose everything if you don't have insurance. So expected value, this is a complicated looking formula, but basically what it's saying to do is take the individual value, positive or negative, for a particular outcome and multiply it by its corresponding probability. And that's what we did in this case here. Right? One outcome was a net loss to the company of 1,000, 10% chance of that. We multiply the probability times that loss. And then 90% of the time they're going to make $500. So you multiply those two numbers too, and then you add these two products together and you get your 50. It's the expected value, right? But again, it's the average value per measurement over the long run. That's the whole idea. And it doesn't necessarily pertain to any particular person. Okay. And here is also somebody who's playing a lottery game. This is another example. And I guess what we'll do to the next time, I'm going to slow up just a little bit. We're going to do some problems next time for the first half of our meeting next time. We were supposed to cover 2 chapters next time. I'm only going to cover one of them. So the first half of Wednesday, we're going to cover the problems pertaining to this chapter. And then the second half will be chapter 16, I believe is the next one. And then we'll catch up sometime later. All right, let's just look at this example and then we'll call it a day. All right, so let me move this out of the way here. Player chooses 1 card from each of 4 suits. A winning card is drawn from each suit. Prizes are awarded based on the number of matches, and the cost to play is $1. So this is some sort of game. It costs you $1 to play. All right, and there are different outcomes. For example, you can win $5,000. You can win $50. You can win $5. You can get a free ticket to play again, or you don't win at all. So those are the 5 possible outcomes of this game. Now, what is the net gain? Well, you paid $1 to enter the game. So if you are the participant, you paid $1, you have to subtract $1 from your winnings, don't you? Now, the only thing is with the free ticket, you're not charged $1. You're basically given another ticket, and you don't have to pay $1. All right. So if you win a 5,000, your net gain's 4,999 because you're subtracting $1 that you paid. 50, it's $49 your net gain. If you win 5, it's $4. Free ticket, 0, no gain or loss. And if you don't win, you lose $1. All right. Now, here are the probabilities for each of these possibilities. Notice the probability is much lower for the $5,000 prize, and a fairly low one for $50, and one that's a little larger probability, but still pretty low, is the $5 one. Here's the probability of getting a free ticket. Almost, 24% of the people will get a free ticket. And then most of the people, over 70%, 72.6% to be exact, don't win anything. And the question is, what's the expected value or expected average gain or loss for the person playing the game? Well, if this is a game that makes any sense, the expected value is going to be a loss, right? Because whoever's doing this wants to gain money. Whoever's setting up this game, they want to make money from it, right? So how do you figure it out? You take your net gain and you multiply it by the probabilities. Each net gain possibility is multiplied by probabilities. Even the 0 here is multiplied by probability. Of course, that's going to turn out to be 0, right? That's why you don't see it here, by the way. 0 times 0.242 is not shown because we know it's going to be equal to 0. And then you just add up all these products and you get negative 35 cents. So what they're really saying is players will lose an average of 35 cents every time they play this game. On average, if they do it many, many times. That's their average loss over many repetitions of this game. And the lottery commission has to pay out what? We'll only pay out 65 cents for each $1 sold. Okay. I don't know. Wait a minute. Does that make sense? We'll only pay out 65 cents. Yes, because they're on average they're gaining 35 cents. So on average, the players per person over many repetitions, they're going to lose 35 cents on average every time they play. That means the lottery commission's gaining 35 cents for every time the person pays. For every dollar sold, that means they're paying out 65 cents every time they get a dollar. All right, and I think that's it. The last page. There's the last page here. Oh, this is just another. We're going to skip this birthday thing here. It's kind of confusing. These are the formulas. If you are a formula person, these are the formulas for the rules that we've been talking about. So you can look those over, but there's no requirement that you memorize these at all. Whatever I ask you is going to be basically application of these rules, basically doing some calculation. But I'm going to show you again examples of all of this next time, first half of the class, and then we'll get into chapter 16 in the second half of the class. Are there any questions? Otherwise, I'll stop the recording. Anything? No questions? All right, it is 3:15, so that's the end of class. I'll stop the